Welcome back, everyone. So in this video, we're going to learn how to calculate the mean and standard deviation of a sampling distribution, how to work with sampling distributions from normal populations, as well as talk about the importance of the central limit theorem. So let's get started. So recall in chapter 2, we learned about frequency distributions, where we take the values of a particular distribution and then we visualize it with a histogram. So similarly, when we're working with a sampling distribution, this is where we take the distribution of all possible values of a statistic, such as the sample mean, and then for a given sample size that has been randomly selected from a population. So in other words, if we took all of the possible random samples of a particular size and then calculated the sample mean for each one and then graphed it in a histogram, this would be our sampling distribution. So there are several theorems in this chapter that are going to help us working with sampling distributions. These are helpful for you to understand conceptually so that when we're working with the sampling distributions, we understand the underlying principles. So the first theorem is regarding the average value of our sample means. So in other words, for any population, if I took all possible sample means and calculated the average value of them, it's going to be the same as our population. So we can say that mu for our sample mean is the same or equals to as mu for the population mean. Theorem 2 is known as the standard deviation of sample means, also known as our standard error. So if we take all of my possible samples and take their sample means, the standard deviation of these statistics is the population standard deviation divided by the square root of n, or the sample size. So the central limit theorem is foundational when we're dealing with sampling distributions. So let's take a look at the next two theorems. First, Theorem 3 states that if a population is normally distributed, meaning it's bell-shaped, then our sampling distribution of the sample mean is also normally distributed. Therefore, Theorems 1 and 2 would still apply. Now, hopefully, you've had a chance to watch the bunnies and dragons video that was also posted in the module. Theorem 4 states that simple random samples of n observations taken from a population, regardless of the population's distribution, the distribution of sample means is approximately normal. Therefore, Theorems 1 and 2 would still apply here. The sample size does need to be sufficiently large, and the larger it is, the better approximation to the normal distribution. So in the bunnies and dragons video, the central limit theorem was demonstrated through samples of normally distributed bunny weights, as well as the bimodal distribution of dragon wingspans. So the central limit theorem really helps us when we're trying to find the probability of an event. So the underlying population could be uniform, it could be triangular, it could be skewed. So if we have a large enough sample size, the sampling distribution of all sample means is going to be bell-shaped. That means we only need to learn one distribution, and that's the normal distribution, as opposed to having to learn all of the different shapes. So for the central limit to work, the sample size must be sufficiently large. So a conservative definition of sufficiently large sample size is n is greater than or equal to 30. If the population is symmetric, then the sample size can be small and it will still provide a normally distributed sampling distribution. Finally, if the population is highly skewed or irregularly shaped like we saw on the last slide, then the required sample size will be larger. In the last few chapters, we have been converting our x values into z values. So recall we learned about standardizing in chapter 3 originally, and then you saw it again in later chapters. So similarly, we can standardize our sampling distribution into z values. Recall, a z value simply measures how many standard deviations a particular value is away from the mean. So here is a z value formula, and this should look a lot like what we learned in chapter 6. So we'll take the sample mean minus the population mean in the numerator, which is in fact our sampling error. Then in the denominator, we have the population standard deviation divided by the square root of the sample size. That is from Theorem 2, and that is the standard error of the sampling distribution. Let's go ahead and work on practice problem 7.23 from the textbook. So suppose a population is known to be normally distributed, with a population mean of 2,000 and a standard deviation of 230. If a random sample of 8 is selected, calculate the probability that the sample mean will exceed 2,100. So in other words, we want greater than 2,100. So step 1, we want to determine the sample mean we're interested in. So it's stated right here in the problem that the sample mean exceeds 2,100. So that's our starting point. And then we'll notate that as the sample mean here. Now in step 2, we want to define the sampling distribution and make use of theorems 1 and 2. So we know that theorem 1 states that the average of all sample means equals the population mean. So in the story, it says that our population mean equals 2,000. Now theorem 2 denotes that the standard deviation of our sampling distribution is the population standard deviation divided by the square root of our sample size. So it's also defined in the story that the population standard deviation is 230 and the sample size is 8. So we'll take 230 and divide by the square root of 8, and we get 81.32 for the standard error of this sampling distribution. Now, in step 3, we want to define the event of interest. Recall, it said we want to know the probability that the sample mean exceeds 2,100. So exceeds is just another way of saying greater than. So the way we'll write our event of interest is the probability of the sample mean is greater than 2,100, and then we want to calculate that next. Now in step 4, we'll go ahead and plug in everything into our formula to find the z-value for our sample mean. So the sample mean is 2,100 and the population mean is 2,000. Then the standard error that we found previously was 81.32. So in the numerator, 2,100 minus 2,000 gets us the sampling error of 100. Then we're just going to divide the sampling error by the standard error, or 100 divided by 81.32, and we get a z-value of 1.23. So in other words, 2,100 is 1.23 standard deviations away from the mean. So in step 5, we're going to go ahead and use Excel to find the desired probability. So here is a visual of the normal distribution curve, and we are interested in finding the probability of this yellow region here. So I'll go ahead and put the z-value of 1.23 here. We learned in chapter 6 that understanding if we're looking for the probability that is greater than or less than will tell us if we could use the output from Excel directly or apply the complement rule to find the probability of the region to the right. So a reminder, Excel always calculates from left to right for the probability distribution calculations. So in the story, it says we're looking for greater than 2,100. So that tells us we need to use the complement rule here. So we will take 1 minus the function inputs of norm.dist, and then we're going to plug in 1.23, which is our z-value, and then true for cumulative, and we get 0.1093. So therefore, it's a 10.93% chance that the sample mean will exceed 2,100 for this sampling distribution. Well, everyone, that wraps up this video on sampling distributions of the mean and the central limit theorem. In our next video, we'll learn about the sampling distribution for a proportion.